Lab 4 Circuits. The purpose of this experiment was to predict the behavior of circuits using an ideal model. We used multimeters to measure current and voltage, observing how ohmic resistors and capacitors behave in a circuit. Our primary result was the RC time constant. We calculated an experimental RC value of 5.97 seconds, which is very close to the theoretical value of 6 seconds. For this experiment, we defined the circuit as a system, with everything else considered to surroundings. Fundamental physics principles. Before we go further, let's discuss some fundamental principles. We applied the conservation of energy and charge, which tells us that electric charge is conserved in any closed system. We use Kirchhoff's laws, the node rule, which states that the current leaving a node equals the current leaving, and a loop rule, which states that the total potential difference in a closed loop is zero. We also use Ohm's law, the equations for equivalent resistance in series in parallel circuits. The linearized form of our capacitor voltage equation, ln of delta V over delta V naught equals negative P over RC, which describes the discharge rate of the capacitor. Assumptions. We made a few assumptions to simplify calculations. We assumed that the resistance of wires in the ammeter was negligible, allowing us to focus only on the resistance and capacitor. Additionally, we used the equation EMF equals delta V cap plus delta V resistors to describe the potential difference, assuming an ideal energy source. This is the picture of our circuit that we built. In part 1 of the lab, we created a circuit with two 1.5 volt batteries, two resistors of 47 and 100 ohms, and 2 ammeters. Based on our predictions, the current was expected to be 0.02 amps, and this is exactly what we measured. Interestingly, if the setup were reversed, we would still see the same current due to symmetry in the circuit's configuration. In the next part, we replaced one of the ammeters with a voltmeter. By doing so, we created an open circuit with a measured voltage of negative 3 volts and a current of 0 amps. When we closed the circuit, we measured the potential differences across various segments. The total potential difference around the circuit was 0, as expected. The ammeter reading did not change, which confirms that the voltmeter's high resistance prevented current from flowing through it. This graph shows the potential resistance position along the circuit. We observed a drop in voltage across each resistor, consistent with Ohm's law. The gradual decrease in potential along the circuit path matches the theoretical expectations, providing a visual representation of how potential changes in an RC circuit. Next, we connected an ammeter in parallel with a 100 ohm resistor. This change caused less current to flow through the resistor itself, effectively reducing the total resistance to around 47 ohms. This is an example of how parallel connections affect overall resistance in a circuit, demonstrating the behavior of resistors in parallel. In part 3, we explored a circuit with a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 200 mF capacitor. When connected, the 10 ohm bulb initially lit up bright, then dimmed as the capacitor charged. Disconnecting the battery allowed us to observe the capacitor discharging as the bulb gradually dimmed. We record charging times of 10.5 seconds for the 10 ohm bulb and 17.3 seconds for the 20 ohm bulb, with discharge time slightly longer due to the RC characteristics. Data. These are data we collected for our experiment. By calculating the natural log of delta V over delta V naught at each time point, we plotted the results to observe the exponential decay behavior. Our slope of negative 0.167 gave us an RC constant of 5.9 seconds, very close to the theoretical value of 6 seconds. This supports our initial predictions and demonstrates the accuracy of our methods. Now let's discuss some possible errors. While our data was consistent with theory, we could have introduced minor errors in timing measurements. In a real-world setting, additional factors like resistance in wires or slight fluctuations in power supply could introduce discrepancies. However, since this was a simulated circuit, these errors were minimized, so we expect any deviations to be very small. In our discussion, we considered how using a real ammeter and capacitor might differ from an idealized model. A real ammeter has non-zero resistance, which would slightly alter the circuit behavior, reducing the current. Additionally, using a real battery and capacitor will introduce internal resistance, preventing instantaneous charging, unlike the ideal model prediction. These differences highlight how ideal models help simplify analysis, but may not capture the full complexity of real-world circuits. Thank you.